This is the start of Chapter 4 for the APB class. It's titled Forces and Newton's Laws of Motion. And it says here, as this elephant stands on its hind legs to reach some choice morsels, it remains in equilibrium because its weight is balanced by the normal force that the ground exerts on its feet. Equilibrium, weight, and normal force are all concepts discussed in this chapter. So what happens here is the weight of the elephant is straight down toward the center of the earth. That's a force pulling on that elephant. It's a force of gravity. We're going to study that force later on in this chapter. There's also, so that's the force of gravity, F sub g. And there's another force here that we're going to have to know about called the normal force. It's the force that a surface applies to a mass. And in this case, it's straight up. That's our normal force, F sub n. And because this elephant is in equilibrium, those two forces are equal. Another thing we're going to say is that the summation of those two forces add up to 0. So when a mass is in equilibrium, the forces will add up to 0. Now we're going to look at Newton's first law of motion. Now, there's 3 laws. We'll look at the first law. An object continues in a state of rest or in a state of motion at a constant speed along a straight line, unless compelled to change that state by a net force. So an object at rest wants to stay at rest, an object in motion wants to stay in motion, and a straight line is the important part. It will stay in that straight line at a constant speed. So that's Newton's first law. Another way of saying that is that objects have inertia, or actually we say mass has inertia. Newton's first law is sometimes called the law of inertia. Any mass, the larger the mass, the larger the inertia. And inertia is measured by how much mass an object has. Not by its velocity, not by its acceleration, only by its mass. How much mass it has tells you how much inertia it has. So the more mass an object has, the more inertia it has. The second law of motion is F equals ma. Now, if you read this, it says when a net external force F acts on an object of mass m, the acceleration a that results is directly proportional to the net force and has a magnitude that is inversely proportional to the mass. That's just a way of saying F equals ma in words. The direction of the acceleration is the same as the direction of the net force. That's going to be a very important idea. The direction of the acceleration is the same as the direction of the net force. Now, a lot of times you'll see this listed as just F equals ma. But you'll see a sigma sign here put in front of that, a summation sign. That means we're going to add up all the forces in the x direction, then we add up all the forces in the y direction, and we can use this equation F equals ma. So we're going to look at an example of this F equals ma problem. 2 people are pushing a stalled car, as figure 4.5a indicates. The mass of the car is 1,850 kilograms. Mass is always measured in kilograms. One person applies a force of 275 N, and that's newtons. So the unit we use for force is newtons, while the other applies a force of 395 N, which is newtons. Both forces act in the same direction. A third force of 560 newtons also acts on the car in a direction opposite to that in which the people are pushing. This force arises because of friction and the extent to which the pavement opposes the motion of the tires. Find the acceleration of the car. So the first thing we do is draw the picture, which we see a nice picture of a green car here. And then we draw what's called a free body diagram. We take away this body, this car, put a black dot there for the car. And we draw these forces that are acting on this black dot, in other words, acting on this car. So we see that we draw 275 newtons to the right, 395 newtons to the right, and 560 newtons to the left. So we want to find the acceleration of the car, and actually, the only force, the acceleration is acting in the x direction. Now, there are forces here in the y direction. There's the weight of the car is straight down. That's your force of gravity. There's also a normal force straight up. Now those two are equal and opposite to each other. They cancel out. And we're not going to pay any attention to those. We're just going to look at the blue vectors here because that's the direction of the acceleration. So we only look at forces in the same direction as the acceleration. We only look at forces in the x direction here. So what we're going to do is we're going to say, all right, the summation of the forces equals ma in the x direction. So we have this right here. We sum up the forces. We have 275 plus 395 minus 560 because it's in the opposite direction. Gives me a total net force of 110 newtons. And if we use that equation, F equals ma, or they have it rearranged to be A equals the summation of the forces all over m, we have 110 newtons all over 1850 kilograms. So that gives us an acceleration of 0.059 meters per second squared. This equation should be now in your equation sheet. You should put this in your equation sheet. F equals ma. It should be listed under chapter 4 in your equations. The next problem we're going to look at is a man is stranded on a raft. The mass of the man in the raft is 1,300 kilograms, as shown in figure 4.6a. By paddling, he causes an average force P of 17 newtons to be applied to the raft in the direction due east, the positive x direction. The wind also exerts a force A on the raft. This force has a magnitude of 15 newtons and 0.67 degrees north of east. Ignoring any resistance from the water, find the x, y components of the raft's acceleration. So you'll see that this P, this 17 newtons, is in the x direction, so that's all set. But you notice that the A force is at an angle of 15 newtons. So you'll have to break that up into its x and y components. And they show that up here, and in this box up here, how that's being done. They're taking the 15 multiplying by sine of 67, taking the 15 multiplied cosine of 67 to get those x, y components. Now what we're going to do is we're going to add up all the forces in the x direction, look at what the acceleration in the x direction is, add up all the forces in the y direction, look at what the acceleration in the y direction is. So we're going to do exactly that, break these force vectors into their x, y components. They're shown as x, y components. They use the ij unit vector. So I means x direction, j means y direction. So that's just a way of showing this. And so we have set for the P force, we have 17 newtons in the x direction. This right here, this I means x direction. And we have 0 newtons in the j direction. That right there means the y direction, which matches up with this vector right over there. And the A, you break that up and you get 6 newtons in the x direction and 14 newtons in the y direction. So we're going to go ahead and add up the forces in the x, add up the forces in the y. And if you look over here at the left, you get if you sum up those forces in the x, you get 17 plus 6 equals 23. You sum up those forces in the y, you get 0 plus 14 equals 14. Now let's look at the equation. Acceleration equals force over mass. And this is the x direction, remember, and so now we have 23 newtons divided by the mass is 1,300 kilograms. And so we end up with an acceleration in the x direction of 0.018 meters per second squared. We do the exact same thing in the y direction, and our summation of the forces in the y direction was 14 newtons, our mass is 1,300 kilograms, and our acceleration in the y direction is 0.011 meters per second squared. If we wanted to, we could find the resultant of the accelerations. We could have done a squared plus b squared equals c squared to find out what the actual acceleration is. Now we're going to look at Newton's third law of motion. And people know that by the following. Whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude on the first body. Some people know this as for every action there's an equal and opposite reaction. So if you hit the wall with a certain force, the wall hits you back with the exact same force. Somebody hits my shoulder with a certain force, my shoulder hits them back with the exact same force. These two polar bears are pushing on each other. They are pushing on each other with the exact same force. And our last example is, suppose that the mass of the spacecraft in figure 4.7 is 11,000 kilograms. The mass of the astronaut is 92 kilograms. In addition, assume that the astronaut exerts a force of 36 newtons on the spacecraft. Find the accelerations of the spacecraft and the astronaut. So pause this video and see if you can think about what that says. But remember, the push on the spacecraft is the exact same push on the astronaut. So you can do F equals ma for each one. So if you do it for the spaceship, you get the 36 Newton force acting on the spaceship divided by 11,000 kilograms. That's the mass of the spaceship, giving you 0.0033 meters per second squared. And the astronaut has a push of negative 36 newtons in the opposite direction. It has a mass of 92 kilograms, and the acceleration of that astronaut is negative 0.39 meters per second squared. They had exactly the same force acting on each other. The force was exactly the same on the two masses, but one mass was much larger than the other, and that's why the accelerations are very different.